Okay, so welcome back. Let's say you're at that job and your morning tasks were to do what we just did, create molar and percent solutions, make those great stock buffers, and then that postdoc said, hey, go take a to lunch. And you were like, cool, but I don't want Italian food today. I want Chipotle. So you go have your Chipotle lunch, and you're fighting the stomach grumbles now, and we're in the afternoon portion of the day, and the task at hand is to take those stock buffers and make working solutions by performing dilutions. So here we go, labeled section called diluting stock buffers to make working solutions. And yes, there's some rhyming words in there, and I'll spare you the pain of listening to me say that. And we're just going to go right away to a talking point here. When we go from a stock buffer to a working solution, generally speaking, one of the important points is that we're working from higher concentration to lower concentration. And so concentration is key. The stocks are at a higher concentration, but when we use them in experiments, they're going to be at diluted amounts and therefore lower concentrations. Let's take a quick pictorial overview of how that might work. Hey, look at that, voila! It's the sodium chloride we've seen before. You went over to one part of the lab and you went to that chemical shelf and you grabbed the sodium chloride and you created a stock buffer that we're going to keep on the shelf at high concentration, maybe in a vessel that looks like that. You're going to store this in the lab away from the chemicals, maybe at a spot close to your bench. And I really like these 1 liter, and you can see there 1 liter equals 1,000 mils by looking at the bottle. I really like these ones with the orange cap. Orange is a great color, it's a happy color. But you also have the benefit of having that nice tight seal by the screw cap. This has nothing to do with the discussion other than I like lab equipment and it's fun to pick ones you like the best. And so there's one of my favorites, so there. But what we want to do now, we're going to think about going to this new vessel, this new working solution. And this arrow here that I just put in is going to indicate that we want to reduce the concentration of our stock. So we're going from this awesome orange-capped little vessel to potentially something smaller, something you're going to work with during an experiment. And it could be as small as an Eppendorf tube. And so let's say this Eppendorf tube might have a 1 mil volume. You just need a small amount. You need to reduce that concentration of your stock. And it could look like a 1.5 mil Eppendorf tube. Here's another pro tip, and you might see that I strategically placed the tip as if this floating magical tip was pipetting something into that awesome Eppendorf tube, and I did that on purpose for your enjoyment. There's a few reasons why we do this in the way that we're describing, meaning making a stock and then at your bench working from a smaller volume in a test tube, going from the bottle to the Eppendorf tube. And so I'm just going to give you a couple of things to think about. One is you could imagine that if you needed a very, very, very small amount, a very small concentration of sodium chloride, to try to measure it out in a small volume to accommodate 1 mil might be super difficult. We might be talking about unmeasurable quantities, way lower than the milligram amount. And so since we don't have balances that sensitive and that wouldn't be accurate at all, even if we could, we go for accuracy and precision's sake from making higher concentrations using amounts that we can measure easily with the equipment that we have, to then dilutions of it to smaller amounts. So there's one reason. You don't need a high concentration. Another reason is that sometimes when you're doing a dilution, you're moving from one solvent to another. Sometimes compounds that you're creating stock buffers from require a solvent such as ethanol. And you only want the component of ethanol in your working solution to be small, maybe 1/100th of the total volume. So just small microliter amounts because you don't want the ethanol to have any negative effects on anything else in your experiment. This can be important, say, if you're doing microbiology and you want to expose bacteria to a compound that you've made a stock buffer from, but you don't want to expose it to too much ethanol. Luckily, in experiments, we designed controls for that. So if you had situation A, where you made a working solution in an Eppendorf tube of a buffer at a low concentration of a compound, you'd create a buffer control to go with it. So you'd just do the ethanol without whatever you made the compound using. We'll talk about that in class, but for now, let me show you actually how we do this. Let's do some math together and let's make some dilutions. Now that we have the overview, let's put our knowledge to work. Work, 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 work. You can work from home. Oh. I don't know how to delete that. I'll just leave it in there. And if you're laughing, thanks. And if you're laughing harder at what I just put up on the screen, or if you don't know what it is, you're gonna laugh when I tell you that's my drawing of a mouse. And in class, what? It doesn't look like a mouse? It looks like a hunchback? I'm telling you, look, the tail's on the left, the ear's colored in black, there's a 3-whisker theme going on up at the front. That's a mouse. Okay, I don't blame you for laughing. It's the best I could do, so there. Now, in class, our activity is gonna be about comparing data for bacteria that are gonna come out of a potential animal experiment where 2 different mice sets are treated with either a compound called X or a compound called Y. And so let's get kind of familiar with thinking about that and let's make our treatments, okay? So here we go. Compound X. It could be anything. It could be an antibiotic or whatever it might be that we're wondering about its effect on bacteria in the mouse. It's not important right now. But what I do know is that compound X is going to be stored in the lab as a stock buffer at high concentration. Cool, just like everything else we were talking about. Hey, look at there. It happens to be kept at a 100% solution. It might be kept in an Eppendorf tube. I know, we said orange flasks, but not all stock buffers are kept in those. Sometimes they're in small containers. And since compound X is orange, there it is, molecules of compound X, a 100% stock. But you know what? This is about comparing an experiment in the lab class portion where X and Y are evaluated in different mice. So here comes mouse number 2. I rotate it horizontal, they're facing off here. It's another cute mousey, or whatever you think it looks like. And here is then compound Y. And here's a little new wrinkle into how we can make stock buffers, and that is called X. So meaning 250 times what we would want to use in a working solution. All of our working solutions, unless otherwise designated, are desired to be at 1x. So this is 250 times the amount of compound Y that we actually want to put into the mouse. So here's our Eppendorf tube in the lab containing compound Y at 250 times what it needs to be. Now, the goal then would be to put a diluted amount into the mouse. Okay? We don't want to put 100% of compound X in there. It's going to kill that poor little animal right away. And so we have to make a dilution in the lab. Hey, look at that, less molecules. And then we'll add it to the mouse. Similarly, we have to do a dilution of compound Y, and then we add it to the mouse. We already went over why we keep all these compounds and stocks at higher concentration. This is another example of them, a treatment for an animal that needs to be diluted first. Okay? I hope you're with me so far. This setup is a pictorial representation of what we're going to talk about in the lab. Okay, so the question becomes, how do we do this? Let's do a little math. How do we go from a stock buffer to a working solution. I'm going to give you a formula. We're going to do it the long way, and then we're going to do it a little short way, and you can see which you prefer. Either way will get you to the same endpoint. So whichever one makes more sense to you is the one I'd like you to use. So here we go. We've got C1 times V1. Ooh, you might know where I'm heading. Equals dun, 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 C2 times V2. So in this case, the C is concentration and the V is volume. So let's look at the left side of that equation. Concentration 1, volume 1. That is an entire reference to what's in that Eppendorf tube in the lab. That's the stock buffer at 100% or 250 times, depending on which one you're talking about. Okay? What we really want to know then is how much do we need to take? How much of that do we really need to take out of there of the 100% solution or the 250x? That's all the C1 and V1 referring to that. The C2 and V2, well, that's where we want to go. That's that working solution that we need to make before we put it into the mouse. Concentration 2, volume 2. That's reference to working solution. So let's do an example for compound X. All right? So the only number I see is 100%. That's the only thing I know. Before I go any further, which value of those 4 in this little equation is represented by 100%? Where should that go? If you said C1, concentration 1, the concentration of the stock buffer, you got it. Nice work. Work. I need some more information. I need some more numbers. Okay? So, in the lab, you might be given the following piece of information. Here's an example. That postdoc might say, you know what? We actually want to create a 15% working solution. A 15% working solution. 100% is too much to give the animal, but 15% should do the trick. This is the effect we want to look for. And we want to make a small volume. We want to make 1.5 mils, 1.5 mils. And we're going to put that in a solvent called PBS, or phosphate buffered saline for short. Phosphate buffered saline. So what this is saying is, go over to that freezer in the lab, take out the 100%. You've got this Eppendorf tube in your hand. And over here, in your other hand, you have a new Eppendorf tube. And you have to make 1.5 mils of compound X at 15%. These two pieces of numbers I just threw at you, 15% and 1.5 mils, are the working solution side of the equation. One of those is C2 and one of those is V2. And if you said that 15% was concentration 2 and 1.5 mils was V2, well, you'd nailed it. So let's put this all together, okay? In this case, we have the mystery brackets, okay? Look at that. Let's go to work. So we already said where things go. Let's put it down. The stock buffer is represented by C1 and V1. We know we have a stock of 100%. The V1, that's what we're solving for. That's X. That's what we don't know. How much are we going to put into our pipette? How much are we going to take of that 100% to make our dilution? This is where we're heading. We know we want it to be 15%, and we know we want the volume to be 1.5 mils. Before I go any further, let me ask you a question. Does the volume of the stock buffer matter? No, it doesn't. That could be in a mil or 10 mils or 100 mils. It's still 100%. The concentration stays the same regardless of what that volume is. The only time this would matter is if after we solved this V1 and we got an amount to pipette that we didn't have enough in that Eppendorf tube. So let's say you came up with, oh, we need a mil. But in that tube, we only have 500 microliters. We have half of as much as we need. Now you're in trouble and you have to go make more. That's the only time that would matter. It doesn't factor into this math, okay? The volume of compound X at your stock is irrelevant, okay? So here we go. As you see here, you're going to multiply 15% by 1.5 mils, and you're going to divide by 100%. And look at your units. You might have already written those down, just like I said before. When you're solving, write down the units first. You're looking for a volume. We've got everything in mils, and so boom, 15% times 1.5 mils divided by 100% is, quick little calculator here, 0.225 mils. 15 times 1.5 equals whatever divided by 100 equals 0.225 mils. I don't know a lab instrument that I can accurately measure 0.225 mils in, but I do know that if I get a pipette and I convert this to microliters, then I can do that. I can go grab a certain amount here represented by this number in microliters. So let's go all the way back and let's double duty here. We've diluted, that's cool, but let's also convert. So how many microliters is represented by this? 0.225 mils, that's the question. Okay, go ahead and solve that. Pause it right here. Welcome back, and if you said, I need to move that decimal place 3 to the right, because there's going to be more microliters in here, 0.225 mils is equal to 225 microliters, moving it by a power of 10 to the third, 3 decimal points, 3 powers of 10. Well, then you nailed it. So I do have an instrument, a micropipetter, that I can use to grab 225 microliters accurately. And so what we would do is then grab 225 microliters, okay, and then you subtract that from the total volume of 1.5 mils, and the rest of that is your solvent to get 225 microliters representing a 15% solution. And I hope that all made sense. So this is the long form, C1V1 equals C2V2. What do I have? Where am I going? I'm solving for the volume I need to take out of my concentrated stock. So really good job on that. I hope that made sense, and I hope you're excited to then do the next logical step, which would be to repeat this process for compound Y. 250x, hey, that's 250 times too high. 250 times what we want, that's a concentration. So the concentration here is 250x. So you're already thinking to yourself, excellent, I know the C1. I just need to know how much of that thing do I need to pipette. It's 250 times what it needs to be. That's a lot. That's really concentrated. I'm already thinking to myself logically, the answer to this question might be a small number. To go from 250x to my working solution, I might not need that much, right? If it's very, very concentrated right now, and I don't need it to be very concentrated, and I'm using small volumes, then I'm not going to be pipetting very much. So let's show you that. The idea here is to create a 1x working solution, and we'll keep the volume the same for our total volume of a working solution of 1.5 mils, and the solvent again is phosphate buffered saline, or PBS, very commonly used in labs. I'm going to bring down my parenthesis as I did before, and as you may have heard me just say, and we're waiting to write in there anxiously, and I hope you're doing this with me, C1 of my stock, what I have is 250x. And again, I need to solve for V1. I need to know how much do I have to retrieve from that tube in the lab containing a high concentration of compound Y. What am I pipetting here? Now we got to make a working solution before I put it in that mouse. We can't do 250x. Come on, that's crazy talk. Crazy. So we're trying to go to 1x like it says. That's our C2. And we want our total volume of our working solution to be 1.5 mils. I'm looking across. All my units are the same. Those x's are going to cancel out just like the percentages did in the last slide. And I'm solving for V1. What are my units going to be? If you said mils, you're absolutely right. We're going to get a result in mils, which makes sense. We're looking for a volume. How much am I taking volumetrically? So if we do what we did before, multiply and divide, we have 1x times 1.5 mils divided by 250x, which really is 1 times 1.5, which is 1.5, divided by 250, and 1.5 divided by 250 is 0.006. Bring our units down, we have mils. Once again, that's not a pipetable amount using instruments that I know how to use, and I got to convert that to something I do know how to use, and that would be a micropipetter. We got to think microliters. So let's again convert mils to microliters. Go ahead, pause it, work it out. Hey, all right, good job. You probably were thinking, when is he going to come back? I can't wait to hear the answer. Well, the answer is 6 microliters, 3 decimal places to the right. Another conversion using the power of 10 to the third, or 3 powers of 10. So excellent job. Compound Y, C1 V1 equals C2 V2. This is the long way. You can use it to your heart's content. Now, what I'm going to show you is a quicker way, and whichever way you prefer, whichever way is more intuitive, that's the one I want you to use. I mentioned a shortcut alternative to get to the same solution, and as promised, here it is. So let's stick with compound Y. We kind of went through the longer way, the C1 V1 equals C2 V2. Let's go through a bit of a shortcut. And essentially, I'm going to get to a different way of determining V1, which is what we wanted in the first place. So in this case, I'm going to think about this whole exercise of making a dilution just like making a dilution. And so for this, I need a dilution factor, okay? The way to use dilution factors to determine V1 is by the following formula, where volume 1 equals the dilution factor. So basically, the stock buffer to working solution dilution times the V2. What's the total volume that you want to make your working solution at? Okay, so dilution factor times V2. So what in this instance for compound Y is our dilution factor? Well, to determine that, we want to know where we're at and where we're going. And this is the elements of C1 and C2. And they're going to end up in the same spots they were before. It's the same principle, just written a little differently. And so whichever one of these is more intuitive to you, that's one you should use. So the dilution factor here is equal to 1 over 250. 1 over 250. A 250th of the stock buffer. So in other words, we've got our C2, where we want to go, which is 1, over where we started, our C1, which is 250. That's our dilution factor. And if you go to the slide before, you see that eventually your equation, when you did the C1 V1 equals C2 V2, had those numbers exactly as shown here, where 1 is in the numerator and 250 is in the denominator. So let's put this to work. Let's solve for V1, okay? So as stated here, it's the dilution factor times the V2. And so we've got our dilution factor all ready to go. And then we multiply this by our 1.5 mils. So 1 divided by 250 times 1.5 mils is, as you may have suspected, the same 0.006 mils as the slide before, going about it just a slightly different way in your mind of thinking about it, using the same numbers and the same principles to get to the same answer, and therefore, upon conversion, the same 6 microliters. There you go. 2 ways to get to the same answer. Whichever is more straightforward to you is the way you should use. If you have a third way that I haven't used here, that's all good too. Okay? So thanks very, very much for your attention and your focus throughout this, and for excusing the crudity of my drawings of a mouse. Not well done, I know, but I made up for it with the cute pictures of my dog, so there. What I want you to do now is go over to the first problem set and work through those. They go exactly in line with this video set. So thanks a lot, and we'll see you soon.